Hello, and welcome to today's practical session, where we're diving into the fascinating world of waves. In our previous lessons, we explored how waves transfer energy without transferring matter, and we introduced key terms like frequency, wavelength, and speed. But understanding these concepts in theory is one thing, seeing them in action is something else entirely. Today, you'll be conducting two investigations to measure the speed, frequency, and wavelength of waves. First, we'll explore water waves in a ripple tank, where you'll get a hands-on understanding of how waves behave in fluids. Then, we'll move to waves in a stretched string, where we'll investigate standing waves in a solid medium. Before we get started, let's consider the importance of studying waves in the first place. The answer lies in how fundamental they are to the world around us. First, the principles of waves are critical in engineering and technology. Whether it's designing bridges that can withstand wind vibrations or tuning musical instruments for the perfect sound, understanding waves allows engineers to create safer and more efficient systems. Even medical imaging technologies like ultrasounds rely on wave behaviour. Secondly, waves aren't just an abstract concept, they're everywhere. Think about the ripples in a pond, the sound waves that reach your ears, or the light waves that let you see. Understanding waves gives us a deeper appreciation for the physical world and how energy moves through it. Our first experiment uses a ripple tank. Our objective here is to observe and measure the properties of water waves, specifically frequency, wavelength, and speed. To do this, we'll be using a ripple tank, a shallow container filled with water that lets us study waves in real time. We'll also need a power supply, a lamp, a wooden bar, a motor, a paddle, a ruler, and a panel beneath the ripple tank to view the waves. Start by ensuring the tank is set up on a sturdy surface with about 5 millimeters of water. The motorized wooden rod will be used to create waves, and a lamp positioned above or below the tank will project the wave pattern onto the panel. If the wave pattern is hard to see, try dimming the lights in the room. Additionally, if you have access to a strobe light, use it to freeze the waves. This will make counting and measuring much easier. We're now ready to begin the experiment. Here's the method. First, we turn on the motor to generate steady waves in the tank. Adjust the wooden rod if needed to ensure the waves are straight and uniform. We can now observe the wave pattern on the panel. You should see bright and dark areas that correspond to the crests and troughs of the waves. With this in place, we can measure the wavelength by placing a meter ruler at right angles to the wave fronts. Measure the total distance covered by several waves, then divide this distance by the number of waves to calculate the wavelength. For example, suppose there were 25 waves in a distance of 1 meter. The wavelength would be 1 meter divided by 25 waves, which equals 0.04 meters. Next, to determine the frequency, we can count how many waves pass a fixed point in 10 seconds. Divide this count by 10 to find the frequency in hertz. For example, suppose that 50 waves passed 1 point in 10 seconds. 50 divided by 10 equals 5. Therefore, the frequency is 5 Hz. Finally, calculate the speed of the waves using the formula. Wave speed equals frequency times wavelength. For example, if the frequency is 5 Hz and the wavelength distance is 0.04 meters, then the wave speed will be 5 times 0.04, which equals 0.2 meters per second. Your data might look as follows. Now we can move on to the next experiment. Our objective here is to measure the properties of waves in a solid medium and observe the formation of standing waves. For this experiment, we'll need a vibration generator, a power supply, a wooden bridge, a string or elastic cord, a pulley, and some weights. First, we connect the vibration generator to the string. One end of the string is attached to the generator, while the other is stretched taut by a weight hanging over a pulley. A wooden bridge is placed along the string to adjust its vibrating length. Ensure the string is properly secured at both ends and that the weight is sufficient to keep the string tight. With this ready, we can now get into the method. For our first trial, let's remove the wooden bridge so we have a longer distance of string to measure. First, turn on the vibration generator and gradually increase the frequency. Watch as standing waves begin to form. These are patterns where parts of the string, also called the nodes, appear stationary while others, the antinodes, vibrate. In our case, the nodes are the two ends where the string is attached. The antinode is the section which is moving a lot, which is right in the middle. We can see here that we have the simplest standing wave we can get, which looks like one single loop in the string as it moves up and down. Once you have this clear standing wave, we measure the wavelength. Here we can see that we have one loop, but we need to recognize that this is a half wavelength, because the full wavelength would actually look like this. So we need to measure the length of this loop, and then multiply it by 2 to find the full wavelength. We may also get more complex standing waves if we increase the frequency. For example, here we can see 2 loops. So we can measure the length of one loop and multiply by 2 to find the wavelength. Now that we know the frequency and the wavelength, we can calculate the speed of the wave using the formula. Wave speed equals frequency times wavelength. Repeat the experiment with different frequencies to see how this affects the wave speed. Once you've completed the experiment, your results might look as follows. And that concludes our practical. Today, we've explored waves in 2 very different contexts. In the ripple tank, we saw how waves move through water, measuring their speed, frequency, and wavelength. In the vibrating string, we observed standing waves and discovered how frequency affects their properties. We also gained a first-hand understanding of how wave speed depends on both frequency and wavelength.